Hey everyone, yeah, I'm Stephen Fitzsimons. I'm Business Development Manager at Calnex, with a particular focus on BT. So you can pop by my office. I tend to be in BT quite often. And I've got Sam Martin on the call with me as well. Sam is the product manager for our network emulation line, and quite specifically on the SNE product line itself. So I'm just going to give you a quick run through about who we are and sort of overview of what we do, and then I'll pass over to Sam for the detail. So Calnex Solutions, we design, produce, and sell test and measurement equipment. Our sort of history has been in the telecoms market. The bulk of our businesses in the past has been on timing and synchronization test and measurement solutions for both lab and field. I myself come from a background in network emulation. I was part of a little startup in Belfast called Jar Technologies that was acquired by Calnex in 2017, 2018. And that product's now been developed sort of enormously over the last 5 or 6 years to become 3 separate, distinct product lines with varying degrees of capabilities. So we're headquartered up in Lithgow in Scotland. And as I mentioned, we've got an office over in Northern Ireland in Belfast. We've got another office in Stevenage with a company acquisition of iTrinegy, which some of you may be familiar with. And then we have local offices in the US, in China, and India. So we've grown quite rapidly over the last 10 years. We now have over 600 customers in 68 different countries. We floated on the London Stock Exchange in 2020 quite successfully. We're ISO 9001 certified. And we've got a number of prestigious awards, particularly the Queen's Award for Enterprise, for International Trade, and for Innovation. We were one of only 7 companies in the UK to get 2 awards in a single year in 2022. So to give you a quick overview of our portfolio, high level. So we have 3 sort of distinct lines of product. We have the Lab Sync product. And these are tools designed for the validation of timing and synchronization equipment in a lab. So validating a master clock or a slave clock or a boundary clock. We have our Field Sync products. And these are primarily designed for measuring network sync and timing in the field. As part of that, there is the Sentry product, which is designed for measuring timing and synchronization and monitoring timing and synchronization in data center or fixed positions. And then the product line we're going to talk about today is Cloud and IT, and this encompasses our network emulator products. So we have the Atero 100 gig, which is an FPGA full line rate network emulator, point to point. And we have the SNE Family line, which we'll be discussing today. And that consists of a sort of an entry level SNE, the SNE-X, which increases the port density up to 28 ports in a single box and offers higher line rate. Then we have the SNE Ignite, which is FPGA based and specifically designed for the front-haul telecom market. And then we have the NE1 product line that we acquired from iTrinegy, and this is more focused on software-defined applications, and primarily, particular use for customers that don't have a whole lot of network knowledge. The NE1 is capable of spinning out network links with a click of a button, like a satellite link or a 5G link, etc. So that's just a very quick overview of all of our products and who we are. And now I'm going to pass over to Sam for the detail of today's session.
Thank you, Stephen. So for my part of the presentation today, I'm going to cover 2 different topics. The first part will be focused on 5G services and that challenge around consistency. And then the second half will be focused on how to emulate effectively those conditions that the 5G services are required to run under. So if we go right back to the very start of 5G and just a really kind of high level overview of where 5G was originally promising to head, and it was that vision around an ever more connected world. Mobile telecoms and our mobile phones were always one use case of 5G. They were the main one behind 4G. But now we're seeing companies, individuals, and everyone get involved in new use cases and exciting opportunities of how to use 5G effectively across many different industries. But that broadness of that vision, as much as it sounds lovely when we talk about it, represents a very major challenge to the engineering teams involved across from the network operator side, all the way through delivering new devices and applications, And that challenge is really what we're going to talk about today, of how we focus on low latency, but the consistency of these networks is really going to drive the success of 5G services and all the applications that entails. If we take the URLLC group of use cases, so that's the ultra reliable low latency communications, and that group of use cases and that group of markets represent a very broad set of use cases, but they all have very different requirements in what they need a 5G network and other types of networks to perform under. Each of the applications is slightly different, and some require super low latency, others require a very tight operating window. But these use cases and markets represent a very significant challenge, because these applications weren't traditionally developed to run over a mobile network. They're always used to being in that controlled environment. And now that we step out of that comfort zone into a mobile network or a more distributed approach to delivering these services, a lot more variability is introduced, and that's where it can start to struggle. This was a study done by Spirent into enterprise customers and what they are looking for when it comes to 5G, and whether they want just a very low latency that operators can deliver most of the time versus a guaranteed window where latency will stay within. And the majority of customers came back and said that they would love to be within that consistent window where they have a slightly higher intrinsic latency, but it is kept within a very controlled segment. And that's where these applications in that URLLC bubble need to be. It's only useful for those applications if they stay within that window. If they keep dropping out or the latency varies too much, the applications will struggle to perform in those situations. And it is that pitch around near real-time communication that really drives URLLC and those applications. So that if that communication is broken at any point, then those applications struggle. And we've got a live demo later on here to show that, also the effects of consistency on those networks. So if we take this enterprise study and we take it a bit further, I'm going to bring across a cloud gaming use case. And this use case will demonstrate that difference between keeping latency very low versus an inconsistent fluctuating latency, and how it all pans out and affects a very tough use case. I'm going to focus on VR for this, as it's a very tough use case to deliver, but also it can demonstrate very visually what happens when we drop out of a good operating window. So this was a quote from that same study, and the very good point I'd like to raise here is the brain can adapt to some latency but can't adapt to jitter. And that's the key point when it comes to things like VR, autonomous driving, everything that requires that back-end server to be very responsive. With VR, you'll see the motion sickness come in as we go through, and we'll talk about that then more on the next slide here. So for those who aren't particularly familiar with how VR works and how it's delivered, motion to photon is the main metric for performance and immersiveness in a VR headset. So we have two screens, one for each eye, and as I move my head with a headset or I have controller input, those screens will update with that entire 360 field of view as the headset moves. And that motion to photon is really just from the user movement to something being rendered on the screen. Traditionally, VR would do that on the device or very closely to a PC located at home and would just stream data to the headset. What we're increasingly seeing is these manufacturers and application providers move all that services to the cloud, all that processing to the cloud side, and that is their target within the next few years, is to get all that processing done in a data center. And that introduces a far greater challenge to those headset manufacturers and also to the networks that are carrying all this traffic. Latency needs to stay within those controlled windows. Otherwise, if you fall out, the headset will introduce a motion sickness kind of effect, and we'll see that on the next slide. The other challenge here is that although we have a very tight latency problem and a very tight latency requirements, these applications also require quite a high bandwidth as the quality increases. So we're adding a lot more traffic to the network and also expecting requirements to be very, very finely and tightly controlled. So before I hit play here, on the left-hand side, I've got a 10 millisecond round trip delay applied to the VR headset. So I'm playing a game here, and on the left-hand side, you'll see just a static delay. It's not going to change. On the right-hand side, what I'm doing is I'm climbing that delay from 30 milliseconds round trip, 40 and above. And you'll see as I climb, you'll see the gameplay start to degrade. It's quite a high round trip latency on the right-hand side, but we'll get to the point in a wee second of how that flows. So you can see on the left screen there, the 10 milliseconds round trip gameplay is fine. And the same on the right hand side, it's a little bit jittery, it's a little bit of latency there, but it's not unplayable. But as we increase that latency beyond the 40 milliseconds, now you see I've lost my 360-degree vision. Every time I turn my head, I've lost that vision around both sides. Now with the headset on, this was a very horrible gaming experience. I remember having to sit for a few hours with the headset off just to relax and get the kind of motion sickness away. But that's a very extreme scenario of how increasing delay will cause an application to fail. And that is a traditional way of testing the network emulation, but it isn't quite enough. And what this next slide will show you is how an inconsistent latency can have the same effect as a very high latency. And that variation and that inconsistency can really destroy an application like this. So we've got on the left-hand side, we have our 10 millisecond delay. And what we're doing on the right is we're varying that latency very quickly between different operating windows. So it's within a very tight window, and that window fluctuates quite a lot, and it drops out every so often and back in. But we're getting a very similar user experience to the very high 40 millisecond delay scenario. And that is where this consistency matters comes in. For all these applications, VR is a low risk scenario. It's a gaming scenario, but with these connected cities, autonomous driving, the responses of vehicles, the responses of lots of different devices are now going to matter in a way that's with a lot more serious consequences of something like gaming. But these new applications and these new markets are all very dependent on user uptake. They're all very new technologies, and a strong launch is required. We've seen many products fail that have tried to bring cloud gaming services or new technologies to market, and when their initial launch was difficult due to network conditions, we've seen those technologies get shied away from and discontinued. And with some of the exciting 5G use cases, we don't want to see that happen. We want to see some very new use cases come through. So just to recap that kind of initial phase, we've got a very strong, difficult challenge to face when it comes to delivering 5G services. We saw the application that when we took that static emulation approach, we raised the latency, we saw the application fail, but we were able to get the same failure at a lower rate of latency just by varying and increasing that jitter of the latency. But everyone needs to work together to make this actually happen for all these services. It's not just on the network operators to provide a robust network. It is up to the application providers and device manufacturers to ensure that their applications are robustly tested to handle the times when a network is under stress. So the key points from here is that 5G services are very highly sensitive applications, and they need consistent network requirements to perform well. And static network testing is not enough to stress the applications. And for a solution to solve this needs to be able to do that static dynamic testing. It's a good use case, a good test case, but at the same time, it also needs to be able to dynamically model those real world conditions that we're going to face with 5G and other network architectures. So the next part of this presentation then is going through how we can model those networks accurately using our SNE product line. And I'll be talking about a performance-based digital twin. And what I mean by that is that the SNE and those emulators will emulate the conditions of the network from point to point and take the performance characteristics of a real world network and properly bring that into the lab. So here we have, just to be exact, rather, to get us kind of our thoughts going about what networks actually are, how they face them in the field. We know that network conditions vary in real life. We all know that. That's not a groundbreaking statement. But why should the emulation in our labs be any different? Why do we set static delays and static drops? We should be doing a dynamic modeling and bring it as close to the real world as possible. What we also need to do is to consider the needs of test engineers when we do that. When we bring in those real world variable conditions, we also have to provide a way for test engineers to have repeatable and reproducible test cases. And that's what we focused on with the SNE, is to bring those two together, to bring the variation of the real world into the lab, but also in a way that is repeatable and reproducible for test engineers. So here on this diagram on the left here is just that kind of static emulation we saw in the first set of videos, where we set a static delay to 10 milliseconds, a static loss, and a static narrow range of jitter. And yes, we'd have lots of test cases at different kind of failure points. You'd step that up like we did in the video, and then you'd find the failure point, and then you can resolve issues in applications. But the bit that really stresses these applications and devices is that dynamic emulation, which is what we're trying to achieve with the SNE, is that we want that variation, different operating windows at different times. You'll have low bandwidth scenarios where you'll have great network performance. You'll have some high bandwidth scenarios where things get a bit strained. And all those scenarios need tested thoroughly for all devices and applications that are going to run across these networks. And that is that model of varying delay, varying packet drop, and varying jitter is what we're trying to achieve here with the SNE. And the SNEs all come with that dynamic modeling. And you can use various data sources to create those models within the SNE. You could take a measurement from the real world. You could create a hypothetical or a standards-based scenario, or you can also accurately recreate a customer failure scenario second by second as it happened and have that as a test case where all you need to do is press play on in the SNE. We have import and export on a CSV file format, so you can just import your data straight into the SNE and it will handle creating the model for you. And that we think is a very powerful feature to bring those that digital twinning to a new level of creating a real network in a box. Essentially, is the pitch behind that. And I'm just going to focus a little bit on that last point there for accurately recreating a customer failure scenario. So we can model a network pre-deployment or monitor a network that exists in it's already been deployed and exists in the real world. But when something happens for a customer, something goes wrong for an application or device, and you know the network conditions that happened, you can rebuild that in the lab. And here's an example we've had recently where a leading network operator received a very heavy fine for an outage related to emergency calls. And the quote for what happened here was it was a temporary routing flaw in a single location and 2 previously undetected flaws in third-party software. Now, some pre-deployment testing of that software would have really helped make sure this issue didn't happen in the first place. But now that it did, you can use the SNE to rebuild that scenario, not only to add to your test plan to further test, but also verify that the issues in the third-party apps were fixed by those companies and how to verify all that is being resolved. So I put here just a rough workflow of what happened in the customer failure scenario. So when traffic was routed to a different site, latency started to decline. And then that caused a backlog of calls start to build up, which further increased the latency, and then it restricted the bandwidth available on the network. And if we take that sort of workflow and we bring that into the SNE, then we can recreate that with our impairments. And this is a screenshot of our user interface and how that network modeling that we've talked about before works in the SNE. So those who haven't seen the SNE interface before, we have what we call impairments, which are these red icons here. And these 2 blue ones are traffic generation sources. So we have a PCAP replay down at the bottom here and a background traffic generator at the top. And each of these impairments is being individually controlled by what we call scenes on the left-hand side here. And in this case, each scene is a 1-second snapshot window. And it will vary the settings on the impairments to make that kind of live network model. But also in this case, we're triggering the start point for different impairments to represent the scenario shown above and how that customer use case could just be replayed now. So in here we have our traffic rerouted to a different site. So that one we raise the intrinsic latency, which was that high latency scenario. And then as the backlog of calls comes in, we start up the traffic generation sources. We restrict the available bandwidth in the pipe by flooding it. And then we increase the latency further after that. And then we turn on our bandwidth throttle and we start throttling the traffic further to really emphasize that scenario. And what that does then is creates that test case that can be replayed time and time again for those customers. And also they can use it then to verify that those third-party apps fixed the issue that they had in the first place and build robustness into their networks. So once you have those network models, then if we go back to our test engineer, what they now have is they have a series of highly accurate network models that represent the real world as closely as possible. And each one of those test cases that you create with the SNE, whether it's a static map or a varying dynamic model, is reproducible every single time you press play. It will provide the same impairments on the traffic time and time again. And that will allow test engineers not only when they find an issue, bring it to their engineers and reproduce the issue time and again. It's also repeatable in terms of running that test test over and over again for their test plans. And I think that's the main bit at the bottom there is the SNE produces a performance-based digital twin. Digital twins use a lot these days to describe different things for simulation and other aspects, but for emulation, we're emulating the performance characteristics of a network that really is the heart of what a network is and how that brings through into the lab. And just to close off here then, I'm going to talk a wee bit, very high level, about the 3 products in the SNE family. I know Stephen mentioned other products at Calnex, but the ones that I work mainly with are these 3 here. So the SNEs are entry level, which is focused on creating a high performance unit in a very small 2U form factor. SNEX goes a different direction, and it's focused on flexibility and bringing in 100 gig performance for real world packet mixes, but also doing emulation at scale to allow customers to really ramp up their test plans and run lots of tests through the unit all simultaneously. And that's where the 28 ports comes from. And it's just launched there last month. So it's a new product, and it's sitting at a very exciting part of its journey. It's just at the very start, and a lot more changes and developments along that flexible simultaneous test capacity route will be following shortly. And SNE Ignite then is our front-haul focused high performance emulator that really focuses on that really low PDV syncing performance side of network emulation. And that's the product family. It will continue to grow and continue to expand. It has done so rapidly the last few years, and will be keeping up for the next few months and years.